This is lesson 1 of Dynamic Systems How-To series. We'll see Simple Electric Dynamic System, RC circuit. This presentation is about RC circuit, a basic dynamic system from the series Dynamic Systems How-To. You will find in this speech fundamentals of RC circuit with applications, time response with step and impulse inputs, frequency response at low, high, and cutoff frequencies, computational simulations, experimental real data graphics. Connecting a resistor in series with a capacitor forms a dynamic system called the RC series circuit. Voltages Vin and Vout are respectively input and output of this dynamic system. We can cite several applications for this circuit, among which are capacitor charge-based timers, circuits for sampling and holding data in computer acquisition systems, filters to reduce the effects of high-frequency noise, low-pass filters. Let's take a look at these applications in some detail. Capacitor charge-based timers. One method that can be used to study the RC circuit as a timer is its step response with the capacitor initially discharged. To do this, we apply a voltage to the RC circuit input just as if we were turning on a flashlight switch. The input suddenly rises from 0 to 100% of the source voltage. At this moment, an electric current appears in the circuit that flows through the resistor towards the capacitor. When crossed by this current, the capacitor receives electric charge, and the voltage on the capacitor increases gradually with the increase of its charge. This causes the voltage on the resistor to decrease over time as the input voltage remains constant while the voltage on the capacitor increases. By Ohm's first law, we notice that the current flowing through the resistor is decreasing over time and thus the capacitor is charged more and more slowly. In a limiting situation where the elapsed time is sufficient to no longer perceive the current flowing through the circuit, the capacitor has a voltage equal to that of the source. Before the next example, we show the step response of a real RC circuit. These are experimental real data graphics. Circuits for sampling and holding data in computer acquisition systems. Data acquisition systems perform sampling and holding of a signal to enable AD conversion. The capacitor charging sampling process should be fast enough so that the voltage on the capacitor approaches the input voltage value while the switch remains closed. The capacitor discharge process during holding should be slow enough that the voltage on the capacitor is considered constant as long as the switch remains open. To analyze the capacitor discharge process, we can use its impulse response. After the pulse occurs, the capacitor has a voltage due to the charge transferred in the sample. In the next few moments, the input voltage is 0 and the current now flows through the resistor to the source. The capacitor charge decreases over time, causing its voltage and current to decrease. In this process, the capacitor is discharged more and more slowly, and in a limited situation, the current will be 0 and the capacitor will have 0 voltage. Now, before the next application, we show the impulse response of a real RC circuit. We see experimental real data graphics. Filters to reduce the effects of high-frequency noise, low-pass filters. Low-pass filters block out high-frequency noise and allow low-frequency signals to pass through. The analysis of this property of the RC circuit is included in the study of the frequency response of dynamic systems. At low frequencies, the capacitor has high reactance and the current in the circuit is practically 0. Therefore, the voltage on the resistor is practically 0. The input and output sinusoidal voltages are almost equal in amplitude and are practically in phase. Sinusoidal input and output graphics at low frequency of a real RC circuit. At high frequencies, the capacitor has low reactance and current is limited by the resistor. The voltage on the resistor is roughly equal to the input voltage. The sinusoidal current is obtained by applying the first Ohm law on the resistor. The output sinusoidal voltage is low amplitude and is 90 degrees behind the input. Sinusoidal input and output graphics at high frequency of a real RC circuit. There is, however, a frequency value at which the resistor and capacitor have the same voltage amplitude. It's called the cutoff frequency Fc because signals with frequency above this value are attenuated and those below are transferred to the output. The output voltage is equal to the input divided by square root of 2, and the electric power obtained in a resistor R by applying this output is that obtained with the input sinusoidal voltage divided by 2. The output sinusoidal voltage is delayed 45 degrees from the input. This explains why the RC series circuit with output voltage over the capacitor is called a delay network. Sinusoidal input and output graphics at cutoff frequencies of a real RC circuit. To summarize the operation of this dynamic system as a low-pass filter, we analyze its frequency response through the modulo and phase Bode diagrams. These graphics are obtained by computational simulation. This was our first presentation on the series Dynamic Systems How-To. Thank you for reading and watching.